The universe is one of the most profound and mysterious subjects that the human mind has ever attempted to comprehend. When we look up at the night sky, we see stars, planets, and the faint smudge of distant galaxies, and it is natural to wonder, where does all of this end? Is there an edge somewhere out there? A boundary beyond which nothing exists? And if there is such an edge, why can we not simply point our most powerful telescopes in its direction and see it? The answer to these questions is far more fascinating and counterintuitive than most people realize. And it reaches into the deepest foundations of physics, cosmology, and our very understanding of space and time. To truly grasp why it is impossible to see the edge of the universe, we must first dismantle nearly every intuitive assumption we carry about the nature of space, light, distance, and existence itself. Let us begin with something that seems simple, the concept of an edge. When we think of any object in everyday life, whether it is a table, a room, a country, or even a planet, we understand intuitively that it has boundaries. A table ends where its surface meets the air around it. A country ends at its political borders. A planet ends where its atmosphere fades into the vacuum of space. Our entire sensory experience of the world is built around the idea that things have limits, that there is always a place where one thing stops and something else begins. This intuition is so deeply embedded in our thinking that it feels almost absurd to question it. Surely the universe, as enormous as it is, must also have some kind of boundary. Surely there must be a place where space itself simply stops. But here is where things become genuinely strange. The universe does not behave like the objects we encounter in everyday life. The rules that govern the large-scale structure of the cosmos are fundamentally different from the rules that govern the objects on a table or the borders of a country. And when we start to examine what modern physics and cosmology actually tell us about the universe, we find that the concept of an edge, at least in the way we normally think about it, may not apply to the universe at all. The universe might be finite in size and yet have no edge. It might be infinite and extend forever in all directions. Or it might be something so geometrically strange that neither of those descriptions quite captures its true nature. What we can say with confidence is that, regardless of which of these possibilities is correct, seeing the edge of the universe is impossible. And the reasons for this impossibility are layered, deep, and extraordinarily illuminating. To understand why, we need to start with light. Light is the messenger of the cosmos. Everything we know about the universe beyond our immediate surroundings comes to us in the form of electromagnetic radiation. Whether it is visible light, radio waves, X-rays, or microwaves, our telescopes, regardless of how sophisticated they become, are fundamentally devices for collecting light. And light, despite being the fastest thing in the universe, still has a finite speed. It travels at approximately 299,792 kilometers per second, which is extraordinarily fast by any human standard, but is nonetheless a speed, a rate, and not an instantaneous connection between 2 points. This seemingly simple fact has enormous consequences for what we can and cannot see. When light travels from a distant object to our eyes or our telescopes, it takes time to make that journey. The light from the sun takes about 8 minutes to reach Earth. So when we look at the sun, we are seeing it as it was 8 minutes ago. The light from the nearest star beyond our sun, Proxima Centauri, takes about 4 years to reach us. So we see that star as it was 4 years in the past. The light from the Andromeda Galaxy, the nearest large galaxy to our own Milky Way, takes about 2.5 million years to reach us, meaning we see Andromeda as it appeared 2.5 million years ago, long before the first members of our genus Homo walked the Earth. And the light from the most distant galaxies we have ever detected has been traveling for billions of years before finally arriving at our telescopes. This connection between distance and time is not merely a curiosity. It is absolutely fundamental to understanding the limits of our cosmic vision. When we look out into space, we are looking back in time. The farther away something is, the older the light we receive from it, and the earlier in the history of the universe we are observing. If we could somehow see far enough, we would not see the edge of space, but rather the edge of time. The earliest moments of the universe's existence, when matter as we know it had not yet formed. When the cosmos was a hot, dense, opaque plasma of particles and radiation. This brings us to one of the most important concepts in cosmology, the cosmic microwave background radiation in the very early universe. During the first few 100,000 years after the Big Bang, the universe was so hot and dense that it was opaque. Photons of light could not travel freely because they were constantly being scattered by the dense plasma of charged particles that filled all of space. The universe was essentially like the interior of a star, hot and brilliant but impossible to see through. Then, approximately 380,000 years after the Big Bang, the universe had expanded and cooled enough that electrons and protons could combine to form neutral hydrogen atoms, a moment cosmologists call recombination. With neutral atoms filling the universe instead of free charged particles, the universe became transparent for the first time. Light could finally travel freely through space, and it has been doing so ever since. The light that was released at the moment of recombination is still traveling through the universe today. It has been stretched and cooled by the expansion of space over the past 13.8 billion years, until it now registers as microwave radiation rather than visible light. But it is still detectable, and it has been mapped in extraordinary detail by instruments like the COBE satellite, the WMAP satellite, and more recently the Planck satellite. This cosmic microwave background, or CMB, represents the furthest back in time we can ever see using electromagnetic radiation. It is the cosmic horizon of our vision. Beyond it, in the direction of earlier times and greater distances, the universe was opaque and no light escaped to tell us what was happening. So even if the universe extends infinitely beyond the CMB, we cannot see any further than that wall of ancient light. The CMB is sometimes called the surface of last scattering, precisely because it is the last surface from which light was scattered and then sent freely across the cosmos. When we point our microwave telescopes at the sky, the CMB appears to surround us on all sides, a sphere of ancient light marking the edge of the observable universe. But it is not the edge of the universe itself. It is merely the edge of what is observable to us, and it is an edge imposed not by any physical boundary in space, but by the finite speed of light and the finite age of the universe. Now let us think more carefully about what the observable universe actually is, and why it has the shape and size it does. The observable universe is the region of space from which light has had enough time to reach us since the Big Bang. Since the universe is approximately 13.8 billion years old, one might initially think that the observable universe should extend about 13.8 billion light-years in every direction. But this is where the expansion of the universe introduces another layer of complexity that profoundly affects our cosmic vision. The universe is not static, it is expanding. Edwin Hubble's observations in the 1920s revealed that distant galaxies are moving away from us, and the further away they are, the faster they are receding. This expansion is not like the explosion of a bomb, where fragments fly outward from a central point into a pre-existing space. It is something far stranger. Space itself is expanding. The fabric of space-time is stretching, and galaxies are being carried along with that expansion like raisins in a rising loaf of bread. The raisins themselves are not moving through the bread. Rather, the bread is growing and the raisins are moving apart from each other because of that growth. Because space has been expanding throughout the history of the universe, the light that we receive from distant objects has traveled a path through a changing space. The photons that have been traveling for 13.8 billion years did not travel through static space. They traveled through space that was expanding all around them. This means that the sources of the most ancient light we can detect are now much further away from us than the time it took their light to reach us would naively suggest. The galaxies that emitted the oldest light we can see were much closer to us when they emitted that light billions of years ago. But the expansion of space has since carried them much farther away. By current estimates, the observable universe extends not 13.8 billion light-years in every direction, but approximately 46 billion light-years. The most distant objects we can observe are now roughly 46 billion light-years away from us, even though the light we see from them left when they were much closer. This moving distance of approximately 46 billion light-years defines the size of our observable universe, often called the Hubble volume or the particle horizon. It is a sphere centered on Earth, or more precisely centered on our location in the universe, because any observer anywhere in the universe would define their own observable universe centered on their own location. This is a crucial point. The observable universe is observer-dependent. An alien civilization on a planet 10 billion light-years away from Earth would have their own observable universe centered on their location, overlapping with ours but extending in directions we cannot see. There is no single privileged center of the universe. Every point in space is equally the center of its own observable universe. This observer dependence is one of the first hints that the edge of the observable universe is not really an edge of the universe in any physically meaningful sense. The boundary of the observable universe is not a wall or a barrier or the end of space. It is simply the limit of what any given observer can see given the age of the universe and the speed of light. Beyond the observable universe, space almost certainly continues. The question is how far it continues and whether it ever truly ends. Here we encounter one of the deepest and most unresolved questions in cosmology. Is the universe finite or infinite? Remarkably, despite all of the extraordinary advances in modern physics and astronomy, we do not know the answer to this question. Both possibilities are consistent with our current observations, and with the mathematical framework of general relativity that describes the large-scale structure of spacetime. And in either case, for different reasons, we cannot see the edge of the universe. If the universe is infinite, then the answer is straightforward, even if the concept of infinity is itself deeply challenging to the human imagination. An infinite universe has no edge because it never ends. There is no boundary to reach, no wall to peer beyond. Space extends forever in all directions, filled with matter and energy distributed in roughly the same way everywhere on the largest scales. In an infinite universe, the observable universe is just a tiny, finite sphere embedded in an infinite sea of space, like a small bubble in an endless ocean. No matter how far we traveled or how powerful our telescopes became, there would always be more space beyond, more galaxies, more stars, more planets, stretching on without limit. An infinite universe cannot have an edge by definition, so the question of seeing its edge does not even arise. But what if the universe is finite? Many people assume that a finite universe must have an edge because in everyday experience, finite objects have boundaries. But this assumption reflects a failure to consider the full range of geometrical possibilities that modern mathematics and physics make available. A finite universe does not need to have an edge. Consider the surface of a sphere, such as the surface of the Earth. The Earth's surface is finite in area. You can measure it precisely, but it has no edge. If you walk in any direction on the surface of the Earth, you will never reach a boundary. You will eventually come back to where you started, having circumnavigated the globe. But you will never step off the edge of the Earth's surface. This is because the surface of the Earth is a two-dimensional surface with positive curvature, and that curvature closes it back on itself. Now, our universe exists in 3 spatial dimensions, and the question is whether those 3 dimensions might be curved in an analogous way. Just as the two-dimensional surface of a sphere is a finite, unbounded space, a 3-dimensional universe could be curved in such a way that it is finite in volume but has no boundary. If you were to travel in a perfectly straight line across such a universe, you would eventually return to your starting point without ever reaching a wall or an edge. Such a universe would be finite but edgeless, and it would be impossible to see its edge, not because the edge is hidden or beyond our reach, but because no edge exists. The question of the universe's curvature is something that cosmologists have studied intensively, particularly by analyzing the cosmic microwave background. The CMB encodes information about the geometry of the universe in the precise pattern of temperature fluctuations that Planck and other satellites have mapped. In a universe with positive curvature, like a sphere, these fluctuations would show certain patterns. In a universe with negative curvature, like a saddle shape, they would show different patterns. And in a universe with flat geometry, the patterns would look different still. The current observations suggest that the universe is remarkably flat, with any curvature being so small as to be undetectable with current instruments. A flat universe, if it is finite, would have a much larger minimum size than the observable universe, meaning that even in a finite flat universe we cannot see anywhere near far enough to loop all the way around and come back to our starting point. And if the universe is perfectly flat and infinite, then it has no edge at all. But even setting aside the global topology and geometry of the universe, there is another profound reason why seeing the edge of the universe is impossible, one that arises from the dynamics of cosmic expansion and is one of the most astonishing discoveries in the history of science. In 1998, 2 independent research teams studying distant supernova made an observation that shook the foundations of cosmology. They found that the expansion of the universe is not slowing down, as most physicists had expected. It is speeding up. The universe is not just expanding, it is accelerating in its expansion. Something is causing the fabric of spacetime to stretch ever faster. And whatever that something is has been given the name dark energy. The implications of this accelerating expansion for the limits of our cosmic vision are extraordinary and deeply unsettling. If the universe's expansion were slowing down or even proceeding at a constant rate, then over time, the light from increasingly distant regions of space would eventually reach us. Our observable universe would grow as time went on, and we would gradually gain access to a larger and larger portion of the cosmos. But because the expansion is accelerating, the opposite is happening. The most distant regions of the universe are receding from us faster and faster. There is a point called the cosmic event horizon, beyond which objects are currently receding from us faster than the speed of light. Now, it is important to be careful here because this sounds like a violation of the cosmic speed limit, but it is not. The objects beyond the event horizon are not themselves moving through space faster than light. Rather, the space between us and them is expanding so rapidly that it amounts to the same thing. The distance between us and them is increasing faster than light can cross it. This is allowed by general relativity because it is space itself that is expanding, not objects moving through space. The speed of light limit applies to motion through space, not to the expansion of space itself. The practical consequence is that any photon emitted by an object beyond the cosmic event horizon will never reach us. The expanding space will always carry the destination point away faster than the photon can travel toward it. And this means that over time, the observable universe is not growing. In the very long run, it is actually shrinking as the universe continues to accelerate in its expansion. More and more of the currently observable universe will be carried beyond the event horizon. Galaxies that are currently visible to us will gradually redshift beyond detectability and eventually pass beyond the horizon, disappearing from our cosmic view forever. In the far future, an observer in our galaxy would look out at a universe that appears increasingly empty, with only the gravitationally bound local group of galaxies remaining visible. The vast majority of the universe will have receded beyond all possibility of observation. This accelerating expansion adds yet another layer of impossibility to the idea of seeing the edge of the universe. Not only is the observable universe bounded by the CMB on one side and the finite age of the universe on another, but the accelerating expansion is actively limiting and reducing our cosmic window. The universe is effectively becoming more and more invisible to any single observer over time. Not because of any failure of our technology, but because of the fundamental dynamics of spacetime itself. Let us now think about another angle on this problem. One that involves the very strange behavior of space near the beginning of the universe. If we could somehow trace the history of the observable universe back to its earliest moments, we would find that the entire observable universe was once compressed into an extraordinarily small region of space. At the moment of the Big Bang, the universe began in an extraordinarily hot, dense state, and it has been expanding ever since. The observable universe, all 46 billion light-years of it in every direction, was once contained in a region smaller than an atom. But the Big Bang does not represent a boundary of space in the way that a wall or a surface represents a boundary of an object. The Big Bang is more properly understood as a boundary in time, a moment before which the laws of physics as we currently understand them break down and our descriptions lose their meaning. General relativity predicts a singularity at the very beginning, a point of infinite density and temperature at which the mathematical equations stop making sense. But this singularity is not a place in space. It is a moment in time. Every point in space began at the Big Bang. There is no special location that was the center of the Big Bang. No place you could travel to and say, this is where it all started. The Big Bang happened everywhere simultaneously, at every point in the universe at once. This is another deeply counterintuitive aspect of cosmology that confounds our everyday intuitions. We tend to imagine the Big Bang as an explosion happening at a specific point in space with matter and energy flying outward in all directions. But this picture is wrong. The Big Bang was the beginning of space itself, not an event occurring within a pre-existing space. There was no point of origin, no center of the explosion, no place outside the universe where the explosion took place. Space came into being with the Big Bang, and it has been expanding ever since. Understanding this helps clarify why the edge of the universe is not simply the place where the Big Bang happened, and from which the universe is expanding outward. The universe is not expanding into anything. There is no pre-existing empty space into which the galaxies are rushing. The expansion of the universe is the expansion of space itself. And there is no outside, no empty container into which the universe is growing. If there were such an outside, it would by definition be part of the universe. Now there is one more layer to this story that we must explore, and it involves a theory called cosmic inflation. In the early 1980s, physicists including Alan Guth and Andrei Lin proposed that the very early universe underwent a period of extraordinarily rapid expansion, far faster than the expansion driven by dark energy that we observe today. During this inflationary epoch, which occurred in the first tiny fractions of a second after the Big Bang, the universe expanded exponentially fast, doubling in size over and over again in an almost unimaginably short time. In the blink of an eye, a region of space smaller than a proton was inflated to a scale that dwarfed anything we can currently observe. Inflation is not merely a speculative idea. It makes specific testable predictions about the nature of the CMB and the large-scale distribution of matter in the universe. And many of these predictions have been confirmed by observation. The cosmic microwave background is extraordinarily uniform in temperature across the entire sky, varying by only about 1 part in 100,000. This uniformity is deeply puzzling without inflation, because regions of the sky that appear to be on opposite sides of the observable universe, and which could never have been in causal contact with each other, have virtually identical temperatures. Inflation explains this by proposing that all of the currently observable universe was once a tiny region in causal contact with itself, and that the rapid inflation then stretched this tiny region to cosmic scales, smoothing out any variations and producing the near-perfect uniformity we observe. Inflation also predicts that the universe should be geometrically flat, consistent with current observations, and it predicts that the quantum fluctuations that existed in the pre-inflationary universe were stretched to cosmic scales and became the seeds of the large-scale structure of the universe, the variations in the CMB that eventually grew into galaxies and clusters of galaxies. These predictions are strikingly confirmed by observation, giving us considerable confidence that inflation really did occur. But if inflation occurred, it has profound implications for the size of the total universe and the impossibility of seeing its edge. If the inflationary epoch lasted even slightly longer than the minimum required to explain our observations, then the total universe would be mind-bogglingly larger than the observable universe. Some estimates suggest that the total universe is at least 10 to the power of 23 times larger than the observable universe, and possibly much, much larger than that. Others suggest it could be infinite. In either case, the observable universe, which already seems incomprehensibly vast to us, would be an almost vanishingly small fraction of the total universe. And the edge of the total universe, if it exists at all, would be so far beyond our observational reach as to be effectively at infinite distance from us. Inflation also leads naturally to a concept called eternal inflation, or the multiverse. In many inflationary models, inflation does not stop uniformly everywhere at once. Instead, it stops in some regions, creating bubble universes like ours while continuing to inflate in other regions. This process can go on forever, creating an infinite number of bubble universes, each potentially with different physical laws and constants, spread throughout an eternally inflating background. In such a scenario, our entire observable universe and the vast unobservable region around it would itself be just one bubble in an infinite foam of universes. The edge of our universe would be the boundary between our bubble and the eternally inflating background. But this boundary would be expanding faster than light, forever beyond our reach, even in principle. The multiverse is a deeply controversial idea, partly because it may be inherently untestable. If other universes are beyond our event horizon and the light from them can never reach us, there is no direct observational way to confirm or deny their existence. Some physicists and philosophers argue that this makes the multiverse unscientific, since a good scientific theory must make testable predictions. Others argue that the multiverse is a natural and even necessary consequence of well-tested inflationary models, and that the mere fact of its unobservability does not make it less real or less scientifically valid. This debate touches on deep questions about the nature of science and the limits of what we can know. But regardless of whether the multiverse is real, the basic point stands. The observable universe is a finite sphere of space from which light has reached us, surrounded by a vastly larger universe that we cannot directly observe. And that larger universe may itself be infinite, or may be embedded in something larger still. At every level of this cosmic hierarchy, the edge recedes beyond our grasp. There is yet another dimension to this problem that we should consider, one that comes from the theory of general relativity and its description of how massive objects curve spacetime. Einstein's great insight was that gravity is not a force in the traditional sense, but rather a curvature of space-time caused by mass and energy. The presence of matter causes the fabric of space-time to curve, and other objects move along the curved paths defined by that space-time geometry. This insight, captured in the equations of general relativity, has been confirmed by countless observations. From the bending of light by the sun to the detection of gravitational waves from colliding black holes, general relativity allows for a wide range of possible universe geometries, and the actual geometry of our universe depends on the total amount of matter and energy it contains and how that matter and energy is distributed. The flat geometry suggested by our observations corresponds to a specific density of matter and energy, called the critical density. If the total density of the universe equals the critical density, the universe is flat. If it exceeds the critical density, the universe is positively curved like a sphere. If it falls below the critical density, the universe is negatively curved like a saddle. A positively curved, closed universe would be finite and have no boundary, like the surface of a sphere. In such a universe, if you were to travel in a straight line long enough, you would eventually return to your starting point. A negatively curved, open universe would be infinite and extend forever. A flat universe could be either infinite or finite, depending on its topology. The mathematical structure that describes how it is connected. Our current best measurements suggest that the universe is very close to flat, but the precision of those measurements is not sufficient to determine definitively whether it is exactly flat, slightly positively curved, or slightly negatively curved. Each possibility corresponds to a very different ultimate fate. and a very different answer to whether the universe is truly infinite. But here is the key point. Even if we discovered with certainty that the universe is exactly flat, or that it is positively curved and therefore finite, or any other possibility, the conclusion regarding the visibility of the edge would remain the same. We cannot see it. If the universe is infinite, there is no edge to see. If the universe is finite but edgeless, like a curved closed space, there is still no edge to see. And if the universe is finite with some kind of boundary, that boundary is so far beyond the observable universe, likely by many orders of magnitude, that no light from it could ever reach us. Let us pause here and consider the emotional and philosophical weight of what we are discussing. The impossibility of seeing the edge of the universe is not merely a technical limitation, a problem that future technology might overcome. It is a fundamental, in-principle impossibility rooted in the very nature of space, time, light, and the history of the cosmos. It is a constraint woven into the fabric of reality. No matter how advanced our civilization becomes, no matter how powerful our telescopes, no matter how many generations of scientists dedicate their lives to the question, we will never see the edge of the universe, if indeed an edge exists. We are cosmically quarantined within our observable universe by the laws of physics themselves. This is a genuinely profound realization. Throughout human history, we have repeatedly discovered that the universe is larger and more complex than we previously imagined. The ancient Greeks believed the stars were embedded in a crystalline sphere surrounding the earth, and the edge of the universe was the outer surface of that sphere. With the Copernican revolution, we discovered that the earth is not the center of the cosmos. With telescopes, we discovered that there are billions of stars in our galaxy. With larger telescopes, we discovered that our galaxy is one of billions of galaxies in the observable universe. And now, with our most sophisticated instruments and our most powerful theories, we have discovered that the observable universe itself is likely just a tiny fragment of a much larger, possibly infinite cosmos, and that the true extent of that cosmos is fundamentally beyond our reach. There is a concept in philosophy called epistemic humility, the recognition that the scope of human knowledge has limits and that we should be honest about those limits. The impossibility of seeing the edge of the universe is perhaps the ultimate expression of epistemic humility in science. It tells us not just that we do not know where the edge is, but that we cannot know. That some questions are, in a deep sense, outside the bounds of what empirical science can address. This does not make those questions meaningless or uninteresting. It makes them all the more fascinating, inviting us to use mathematics, logic, and theoretical reasoning to probe the possibilities even when direct observation is impossible. Consider, for instance, the concept of the Hubble volume and how it relates to the broader cosmos. The observable universe contains approximately 2 trillion galaxies, each containing on average hundreds of billions of stars, many of which have planets. The number of potentially habitable planets in the observable universe alone is astronomical beyond any ordinary sense of the word. Yet if the total universe is as large as inflation suggests, the observable universe is an absurdly small sample of the whole. It would be as if you were trying to understand the population of the entire Earth by examining a single grain of sand. The grain might tell you something about the chemistry and physics of the Earth, but it would miss the vast majority of the planet's diversity and structure. This comparison has genuinely startling implications. If the universe is vastly larger than the observable universe, then the patterns and structures we observe within our cosmic neighborhood may not be representative of the universe as a whole. There might be regions of the universe where the large-scale structure is completely different from what we see. There might be regions where the physical constants take different values. If inflation created a landscape of different physical parameters in different parts of the universe, there might even be regions where the laws of physics themselves are different. If the multiverse scenario is correct and different bubble universes nucleated with different underlying physics, we have absolutely no way to test any of these possibilities through direct observation, which is part of what makes them so philosophically provocative. The universe beyond the observable universe is, in a very real sense, a form of scientific blind spot. We know it is there, or at least we have very strong theoretical reasons to believe it is there. But we cannot see it, and we may never be able to probe it directly. It is the ultimate epistemic horizon. Yet even within our observable universe, there are things we cannot see, not just because of the cosmic microwave background horizon, but because of the finite age of the universe and the finite time it takes light to travel. There is a concept called causal disconnection, which refers to the fact that regions of space that are sufficiently separated have never been able to influence each other because light has not had time to travel between them since the Big Bang. The universe contains many regions that are in this sense causally disconnected from each other, and we ourselves are causally disconnected from all regions beyond our Hubble volume. This causal disconnection is deeply connected to the nature of what we call reality. In a sense, the causally connected region of the universe, the region that has been able to influence us and that we have been able to influence, is the only part of the universe that is physically real to us in any practical sense. The rest may as well be fictional, not because it does not exist, but because it has no causal connection to our history or our future. We are embedded in a cosmic bubble of causal connection, and beyond that bubble lies a universe that is, for all practical purposes, beyond reality as we can experience it. This leads to a fascinating question in the philosophy of science. Should we consider regions of the universe beyond our causal horizon to be truly part of the same universe as us, or should they be considered separate entities? If two regions of space can never interact, can never exchange information, can never influence each other in any way, what does it mean to say they are part of the same universe? This question does not have a universally agreed upon answer, and it touches on deep issues in the philosophy of existence, identity, and scientific realism. Some physicists and philosophers argue that the universe, properly defined, should include only the causally connected region, what we have been calling the observable universe. On this view, the unobservable regions beyond the Hubble volume are, in a meaningful sense, different universes, even if they are connected to our universe by a continuous expanse of space. Others argue that the universe should be defined geometrically as all of space, whether or not different regions are in causal contact, and that the various causally disconnected regions are all parts of one vast whole, even if they can never interact. This debate is not merely semantic, it has real implications for how we think about the nature of reality and the scope of physics. If the universe extends far beyond the observable region, then the laws of physics we have discovered and tested in our local cosmic neighborhood may be valid throughout the entire universe. Or they may not be. We have no way to know. This is a source of deep intellectual humility for scientists, a reminder that even our most fundamental and well-tested theories are, in a sense, local knowledge, knowledge verified only within the limited domain of the observable universe. Let us now turn to another aspect of the impossibility of seeing the edge of the universe, one that involves the concept of look-back time and the distinction between the universe as it is now and the universe as we observe it. When we look at the cosmic microwave background, we are seeing the universe as it was 380,000 years after the Big Bang, roughly 13.24 billion years ago. When we look at the most distant galaxies, we are seeing them as they were when the universe was a tiny fraction of its current age. When we look at nearer galaxies, we see them as they were millions or billions of years ago. And when we look at stars in our own galaxy, we see them as they were thousands or even millions of years ago, depending on their distance. This means that our view of the universe is not a snapshot of the universe as it is right now. It is more like a composite image assembled from different eras of cosmic history, with the nearest object showing us the recent past and the most distant object showing us the very ancient past. We can never see the universe as it actually is right now at this present moment across all its vast extent. By the time light from distant regions reaches us, that light is ancient history. The universe we see is a palimpsest, a document written over again and again by light from different cosmic epochs, and we must use our theoretical understanding to piece together what the universe might look like today, far beyond the reach of our instruments. This temporal dimension of cosmic observation adds a further layer to the impossibility of seeing the edge. Even if there were an edge to the universe, and even if it were within the observable universe, the light we would receive from it would be ancient, showing us the edge as it was billions of years ago rather than as it might be now. The universe is not just vast in space, it is vast in time, and our observations are always views into the past. The edge, if it exists, recedes not just spatially but temporally. Now there is one more concept that deserves careful examination. The distinction between the cosmic event horizon and the particle horizon. We have been discussing the particle horizon, which is the boundary of the observable universe, the distance out to which the oldest light we can receive has traveled. But the event horizon is a different concept. The cosmic event horizon is the boundary beyond which events occurring right now can never send a signal to us in the future, no matter how long we wait. It is defined by the future light cone of our current position, taking into account the accelerating expansion of the universe. The particle horizon tells us the limits of our past observations, how far away we can see based on the history of the universe up to now. The event horizon tells us the limits of our future observations, how far away events occurring today can eventually be detected by us. Because of the accelerating expansion of the universe, the cosmic event horizon is smaller than the particle horizon. The universe that is observable to us today is larger than the universe that will ever be observable to us in the future, because the accelerating expansion is steadily shrinking our accessible cosmic volume. This means that the accessible universe is not a fixed entity. It is a shrinking domain. Future generations of cosmologists, if they exist, will have access to less of the universe than we do today. Not because their instruments will be worse, but because the accelerating expansion will have carried more of the universe beyond the event horizon. In the very far future, when the universe has expanded by many orders of magnitude more than it has today, the only structures visible from our galaxy will be those within the local group, the gravitationally bound cluster of galaxies that includes the Milky Way and Andromeda and a few dozen smaller companions. Everything else will be beyond the event horizon, red-shifted into invisibility, gone forever from any possible observation. Future inhabitants of the local group, if any exist, will look out at the sky and see a universe that appears to consist only of a relatively small collection of galaxies embedded in an otherwise empty void. They will have no direct observational evidence of the vast cosmic web of galaxies that we can observe today. And if they lack the theoretical and historical knowledge we have accumulated, they might conclude that the universe is small and relatively simple, confined to just the local group, they would be profoundly, catastrophically wrong about the true nature of the cosmos, and they would have no way to correct their error through observation alone. This thought experiment is more than just a curiosity. It illustrates that what we can observe about the universe depends not just on the laws of physics, but also on when in cosmic history we happen to be observing. We are fortunate to live in an era when the universe is still young enough that the cosmic web of galaxies is visible, when the CMB is still detectable and rich with information about the early universe, and when we have not yet been isolated within the local group by the accelerating expansion. We live, in a sense, in a golden age of cosmological observation, and that age will not last forever. But even in this golden age, the edge of the universe remains utterly beyond our reach. We are surrounded on all sides by the ancient glow of the CMB, which marks not the edge of space but the edge of time, the earliest moment from which electromagnetic radiation can reach us. Beyond that surface of last scattering, the universe existed but was opaque to light, and no photon from that era of cosmic history has reached us. And beyond the era of recombination, all the way back to the Big Bang itself, the universe was entirely opaque to the forms of radiation we typically use for observation. This does not mean we are completely blind to the very early universe. Other messengers can reach us from earlier epochs. Gravitational waves, for instance, propagate through the universe without being scattered by matter, and a background of primordial gravitational waves generated during inflation or other early universe processes might be detectable with sufficiently sensitive instruments, neutrinos, which interact only weakly with matter. Decoupled from the rest of the universe about 1 second after the Big Bang, even earlier than photons, and a cosmic neutrino background analogous to the CMB pervades the universe and in principle could be detected, though the technical challenges of doing so are enormous, and cosmological observations of the large-scale structure of the universe, the distribution of galaxies, galaxy clusters, and the cosmic web, encode information about the physics of the early universe that can be extracted through careful analysis. These alternative windows on the early universe are exciting and are the subject of intense research, but none of them provide a view of the edge of the universe. They give us information about the physics of the very early universe, the first seconds and microseconds after the Big Bang. But they do not tell us about the spatial extent of the universe or reveal any boundary. The universe at the moment of the Big Bang was not a small object in a large empty space. It was, according to our best current understanding, either a very hot and dense finite volume with no boundary or already infinite and uniformly filled with matter and energy from the very beginning. In either case, there was no edge then, and there is no edge now. We should also think about what we mean by seeing in this context. When we say we want to see the edge of the universe, we are assuming that seeing means detecting electromagnetic radiation, light in some form, that has traveled from the edge to our detectors. But electromagnetic radiation travels at the speed of light and is subject to all the constraints we have discussed. The finite age of the universe, the expansion of space, the opacity of the early universe, and the accelerating expansion that limits our future observations. Even if we broadened our concept of seeing to include gravitational waves or neutrinos or some other cosmic messenger, the fundamental limitations would remain. Any physical signal that can carry information about a distant region of space is subject to the laws of physics, which prevent it from traveling faster than light in a vacuum and which therefore impose the same basic limits on what we can observe. Unless, of course, there is some entirely different mode of observation that we have not yet discovered or imagined. The history of science is full of cases where entirely new phenomena were discovered that opened up new observational windows on the universe. The discovery of radio waves opened up radio astronomy. The development of X-ray telescopes revealed a universe full of high-energy processes invisible to optical instruments. The recent detection of gravitational waves has opened the era of gravitational wave astronomy. It is possible, perhaps even likely, that the future holds discoveries we cannot currently anticipate. New forms of observation that reveal aspects of the cosmos currently beyond our reach. But even allowing for such optimism, it is very difficult to see how any new mode of observation could circumvent the fundamental limits imposed by the finite age of the universe and the nature of the Big Bang. The Big Bang is not just a distant event that limits how far we can see. It is the origin of time itself, or at least of the time that we can meaningfully describe with our current physics. There is no time before the Big Bang from which information could reach us because there is, in the usual understanding, no before. And if we cannot receive information from the time before the Big Bang, we cannot receive information from arbitrarily distant regions of space that are beyond the Hubble volume, because those regions are connected to us only through times that exceed the age of the universe. The impossibility of seeing the edge of the universe is in a very deep sense an impossibility of receiving information faster than the expansion of space or earlier than the Big Bang. It is a consequence of causality itself, of the principle that information cannot be transmitted faster than the speed of light and cannot be transmitted from moments before the beginning of time. These are not merely technical limitations. They are the constraints that define what it means for events to be real, for causes to precede effects, and for the universe to be a coherent, consistent place in which science is possible at all. And yet, The impossibility of seeing the edge does not mean that the edge, if it exists, is without significance. The existence or non-existence of a boundary to the universe, the topology and geometry of space on the largest scales, the ultimate fate of the cosmos. These are questions that matter enormously for our understanding of the nature of reality. They are questions that cosmologists take very seriously and that drive much of the theoretical and observational research in the field. We may never be able to answer them definitively through direct observation, but we can constrain the possibilities through our observations of the observable universe and through the internal consistency requirements of our theoretical models. For example, the fact that the universe appears geometrically flat to high precision tells us something important about its overall structure, even if it cannot tell us definitively whether the universe is finite or infinite. The flatness strongly suggests that if the universe is finite, it is very much larger than the observable universe, because any curvature would have been diluted to near undetectability by the enormous size of the cosmos. This is a form of knowledge about the universe beyond the observable horizon, indirect knowledge inferred from what we can see rather than direct observation of what lies beyond. Similarly, our theoretical understanding of inflation and the physics of the early universe gives us constraints on what the larger universe might be like. If inflation occurred in the way that current models suggest, then the universe beyond the observable horizon should look broadly similar to the observable universe in its physical laws and large-scale structure, even if it differs in its specific arrangements of matter and energy. This is because inflation stretched a tiny, causally connected region to enormous scales. So all parts of the inflated universe share the same initial conditions and the same physical laws. This gives us some reason to think that the universe beyond the observable horizon is not completely different from the universe we can observe, even if we can never verify this directly. The story of the universe's edge, or lack thereof, is ultimately a story about the relationship between knowledge and reality. We live in a universe that is, on the largest scales, fundamentally unknowable through direct observation. The true extent of the cosmos, its ultimate shape, its total contents. The question of whether it is finite or infinite, whether it has a boundary or not, all of these questions lie beyond the observational horizon. We are like creatures living at the bottom of a vast ocean, with instruments that can detect the water immediately around us and perhaps some signals from distant regions, but with no way to ever see the surface or the other side. We know the ocean is there. We have strong theoretical reasons to believe it is much larger than the region we can directly detect, but its ultimate extent and nature are beyond our direct experience. This metaphor, however, has one crucial flaw. The ocean has a surface, a physical boundary where water meets air. But the universe, as far as we can tell, has no such boundary, or if it does, the boundary is of a very different nature than the surface of an ocean. The universe's edge, if it exists, is not a surface where space meets something else, because there is nothing outside of space. There is no air above the cosmic ocean, no external environment into which the universe is embedded. The universe is by definition everything that exists, and there can be nothing outside everything. This is perhaps the deepest reason why seeing the edge of the universe is impossible. The very concept of an edge requires something on the other side, a beyond, an outside. And the universe, by its very nature, has no outside. Whatever form the universe takes, whether it is infinite or finite, curved or flat, bounded or unbounded, it is the totality of existence. There is nothing beyond it for an edge to border. The universe is not expanding into anything. It is all there is. And how can something without an outside have an edge? This philosophical point may seem abstract, but it has real physical content. In general relativity, the universe is not a collection of matter distributed throughout a pre-existing empty space. The universe is space-time itself, the four-dimensional fabric of space and time, along with all the matter and energy it contains. Space-time does not exist in anything. It is not located in a higher dimensional void. It simply is, and all of physical reality is contained within it. To ask what is outside the universe, or where the edge of the universe is to ask a question that may be literally meaningless. A question based on a category error, applying the concept of outside or edge to a thing for which those concepts do not apply. Different cultures and different epochs in human history have imagined the edge of the cosmos in different ways. Ancient Babylonian cosmology placed the earth at the center of a flat disk surrounded by a cosmic ocean, with the heavens above and the underworld below. The ancient Greeks imagined a spherical earth surrounded by crystalline spheres carrying the sun, moon, planets, and stars, with the outermost sphere of fixed stars representing the boundary of the cosmos. Medieval European cosmology added theological dimensions to this scheme, with the empyrean heaven, the dwelling place of God located beyond the outermost sphere. Each of these cosmologies provided a kind of edge to the universe, a definite boundary beyond which nothing existed, or beyond which lay a realm of a fundamentally different kind. Modern cosmology has swept away all of these boundaries, replacing them with a universe that may be infinite, that certainly extends far beyond what we can see, and that has no center and no edge that we can point to or travel toward. This is in some ways intellectually unsatisfying because we are creatures who live in a world of edges and centers and boundaries, and our intuitions are tuned for that world. But the universe is not obligated to satisfy our intuitions. It is what it is, And our job as scientists and as curious minds is to try to understand it on its own terms, even when those terms violate every expectation we bring from our everyday experience. The impossibility of seeing the edge of the universe is thus not a failure of science or of technology. It is one of the most profound and beautiful results of the scientific enterprise. A result that tells us something genuinely deep and surprising about the nature of the cosmos. It tells us that the universe is not a finite object in a container. It tells us that time has a beginning in the Big Bang, but space may not have a boundary in the same way. It tells us that the speed of light, while permitting us to observe the universe billions of light years away, also imposes a fundamental horizon that can never be crossed. It tells us that the accelerating expansion of the universe is gradually but inexorably shrinking our cosmic window, making the far future a lonelier and more isolated place than the present. And it tells us that despite all of the extraordinary knowledge we have accumulated about the cosmos, the universe is still full of mysteries that may forever remain beyond our grasp. Perhaps the most remarkable thing about all of this is not the impossibility of seeing the edge, but the fact that we know so much about the universe at all. Using only the laws of physics, mathematics, and the photons that happen to reach our telescopes, we have reconstructed the history of the universe from fractions of a second after the Big Bang to the present day. We have mapped the large-scale structure of the observable universe, identified the major components of its content, measured the rate of its expansion, detected the ancient light of recombination, and begun to probe the very earliest moments of cosmic time. We have done all of this without ever leaving the tiny corner of the cosmos where we happen to live, without ever traveling to the distances our telescopes explore, relying entirely on the information encoded in the light, gravity, and other signals that reach us across the vast expanse of space and time. The edge of the universe, if it exists, will likely remain forever invisible, forever beyond the reach of our instruments and even our future descendants' instruments. But what we can see and what we have learned is already staggering in its scope and beauty. The observable universe is a window of about 46 billion light-years in every direction, filled with trillions of galaxies, each containing billions of stars, embedded in a web of dark matter and dark energy, all evolving according to the same laws of physics that govern the atoms in our bodies and the electricity in our brains. It is more than enough to fill a lifetime, or 1,000 lifetimes of wonder and inquiry. And perhaps that is the most important lesson of all. The impossibility of seeing the edge of the universe does not diminish the magnificence of what is visible. It adds to it. It reminds us that the universe is larger than our instruments, older than our civilization, stranger than our intuitions, and more magnificent than our imaginations can fully encompass. We are small creatures on a small planet in a small corner of an ordinary galaxy in a universe of almost incomprehensible scale. And we are trying with our finite minds and finite instruments to understand the infinite. That we have gotten as far as we have is itself a kind of miracle. A testament to the power of human curiosity and the extraordinary effectiveness of mathematics, and the scientific method in revealing the hidden structures of reality. The edge of the universe, wherever it may be or whether it exists at all, remains hidden from us, not because we have failed to look hard enough, but because the universe itself, through the laws of physics it obeys, ensures that some of its secrets remain forever out of reach. And in that forever unreachable horizon we find not frustration but wonder, not defeat but the enduring invitation to keep asking questions, to keep building better instruments, to keep developing deeper theories, and to keep marveling at the extraordinary fact that we live in a universe so vast, so ancient, and so strange that even after centuries of scientific progress, its edge, if it has one at all, remains as invisible and as mysterious as ever.